In this video, I would like to write 3 more recursive functions for my raw lists. So I want to go through this parts B and C of this testing code. In the previous video, we wrote print list and print reverse, and I think we already have some case to make here that recursion can really help us with these singly linked lists. In this video, I want to write insert at end, add a new node to the end of a list, and then I want to write functions to count the number of elements in a list and to add up the number of elements in a list. So I'm going to begin with insert at end. And we're going to still think about it with that recursive point of view that we used in the previous video, which is if we think about a list, if I give you a pointer to the beginning of a list and the list has at least one node, what I really have is the first node of the list and the rest. That's it. And so I can break that down recursively because this itself, the rest of the list, is itself a smaller linked list. And then I could go into the rest of the list and use the same logic. The rest consists of a node followed by the rest of the rest, and so on all the way down until what's left over is actually an empty list. And so that's my goal, is to use the same logic to write insert at end and then to do count elements and sum list. All right, insert at end. So up here, I've condensed down my print list and print reverse functions from last time. I have insert at front. Now, insert at front doesn't need to be recursive or iterative because adding at the beginning of a list doesn't require iterating over anything. I can just add to the beginning just by performing a couple of local operations. So insert at front still exists. And so what I want to do is, just like before, I want to avoid doing work wherever possible. And I observe, like I did in the iterative sequence, that if the head pointer is equal to null, so if I'm working with an empty list, inserting at the end of an empty list is the same as inserting at the beginning. I'll even write that down. Inserting at the end of an empty list is the same as inserting at the beginning. So as a result, I don't need to write anything for this. I can just call my friend the insert at front function and ask it to handle this for me because I know already that insert at front works. And as usual, if you know that there's a function you can call, just call it. So I call insert at front and then the function ends. So that means down on line 73, I can assume that the list already has at least one element. Okay, at least one, I should say node. Okay, next question. How do I insert at the end of a list that contains that contains at least one element? Okay, I think there are a few cases. So one of them is you have given me a pointer to the only node of my list. So if the head pointer, in this case, if what you gave me as the start node is the end of the list, it's really easy to insert at the end. All I do is add a new node after the one that you gave me. So I just stitch this in out here. All right, so let's actually do that case first. I know how to add it to the end of a very short list. So I know here the list already has at least one node. So that means that I can follow the head pointer and get to a node. If head arrow next equals null PTR, well, I guess that means that the list starting at head has exactly one node already. So adding a new node after that, it shouldn't be too difficult. So I create a new node PTR new node equals, and I call make shared. Make a new node. Because it's going to be the last node in the list when I'm done, its next pointer is going to be null, and its value is going to be the value that was passed in. Okay, it's very similar to the iterative case when I'm creating the new node. And then, because I know that the list that I'm working with only has one node in it, it's pretty easy to attach it. All I do is add it after that very first node. So head arrow next equals new node. All right, so now I know how to insert at the end of a list that contains one node. Okay, so if I'm down, and then I'll do an else. And if I'm down here, that means the list starting at head contains more than one node. Okay, so how do I handle that case? And so that case would be something sort of like this. You've given me a pointer to this node here, the head. This is the node I was told to start from, and it contains more than one element. I have no idea what else is there. There's some other nodes after the node you gave me because I know that the node you gave me isn't the only element of the list. I actually don't care how many elements are left over. Like before, I want to use some recursive decomposition. And I think about this for a minute and I realize, okay, wait a minute. So if the list contains at least two nodes already, then what do I really have? Okay, so I've got the node you gave me. That's this, the current value of head. This would be head arrow next. and it just goes off into the distance. Who knows how long this shorter list is? What is it that I want to accomplish? Well, what I want is when I'm done, I've added a node to the end of this, the rest of my list. And I think, oh, that's annoying. If only there were a function I could call that adds a node to the end of this shorter list. And would you believe it? There is the insert at end function. So I say, well, in this case, I want to insert at the end of the shorter list starting at head arrow next. And I would like to insert the same value as before. And I'm done. So we'll try that out. And as usual, the warnings are fine because they're just functions we haven't gotten to yet. We'll try running this. Okay, so if we scroll down to main, let's take a look. Okay, so in part B, I am adding the element 10 3 times to the end of my list L1. Let me just get this out of the way. And so there we go. And so I do that, and we notice in the output, after the end of part B, sure enough, the list does contain 17, 10, 6, 10, 10, and 10. So I've added the element 10 3 times to the end of L1. Because I want to use the same testing code as the iterative case for fairness reasons, I'm not going to change this. You might want to download the code and verify that if you change these elements to something else, it does indeed still insert at the end of the list. And I claim that it does. Okay, now you might notice this looks a bit scary. Number of elements equals something horrifying. That isn't because the functions are broken, it's because I haven't written them yet. Because I haven't written them, they actually have no return statements, and that means they're returning random garbage. So yes, it's alarming, but don't worry about it, we're just about to get there. The end of part B, which is where we're at, seems to indicate that it is correct. The insert at end function was able to insert at the end of my list by using that recursive decomposition. So I'll mock that up for the first insertion. So I say, here's the beginning of my list, the node containing 17. Insert the node 10 at the end of this list. And the function says, okay, so the list contains more than one element. So in that case, I'll say insert the node 10 at the end of this list. This list contains more than one element. Insert the node 10 at the end of this list. And this is a list that contains only one element. If I give you a pointer to the 6, you're looking at the beginning of a list containing only one element. And so it adds the element 10, I'll just add it here, it adds the element 10 to the end of that list. There we go. And we do that again 2 more times to add the element 10 a total of 3 times. Now I'm going to fix up my diagram. I'd rather use the shorter version of L1 for the sake of my sketch for the next couple of functions. So I now want to write count elements and sum list, these 2 functions. I want to get rid of these hideous return values. So we'll go up and try that. Okay, count elements. And I again try for that recursive decomposition. I say, okay, if you hand me a pointer to nothing, how big is that list? I mean, how big is an empty list? Okay, well, that's pretty easy. So if head is equal to a null pointer, then the number of elements is 0. Great. Well, that wasn't so tough. Okay, what else? So suppose you hand me a pointer to a list containing at least one element. Okay, so there it is. It's got something inside of it. And then we draw it the usual recursive way. So I've got my one element, and then I've got the rest. So this would be the value of, this is what head points to. This is the list starting at head arrow next. How do I count the number of elements in that list? Well, I think the number of elements has to be, well, okay, there's one that I'm looking at, so obviously there's 1, plus the number of elements in the rest. If only I had a function I could call that would count the number of elements in this shorter list. Well, hey, I do, don't I? I could return 1 plus the number of elements in the rest. So head arrow next. And because I'm using head arrow next, I know that the list that the function receives with this recursive call is a tiny bit smaller. And that means if I keep doing this, if I go all the way down, as I count elements, I first count, okay, 17, there's 1, plus the number of elements over here. Okay, so I ask for the number of elements over here. 10, that's 1, plus the number of elements over here. The list that I'm counting gets smaller and smaller until eventually it's empty. And then I just return 0 and I'm done. The recursive process ends at that point. So we look at this and say, I think even though the loop, the version of this that was iterative wasn't too tough, right? We were able to write a loop in only a few lines that counted the number of elements. This is pretty neat. This is pretty elegant. I think it's about the same length, especially if I condense this down into being without removing the curly brackets from this if statement. And I think it's very conceptually beautiful. It makes it a lot more obvious to somebody reading it what's going on. And because there's no need for some for loop with a pointer, there are less places I could make a mistake. Okay, well, let's keep the positive vibes coming here. Let's see if we can write some list. I'm just shamelessly gonna copy count elements. I think to myself, okay, how do I add up the elements? You give me a list. So again, there's 17, and then there's the rest. How do I add these up? Well, what is the sum of a list that has 0 elements? And we talked about this in the iterative case. Actually, I don't like that. I don't think we should be adding up lists with 0 elements, so I'm going to say that's a runtime error. If you try and tell me to add up 0 elements, I don't know what an empty sum is supposed to be. So I'm going to say can't sum an empty list. All right. Okay, what about if you give me a list with only 1 element? So the sum of a list with only 1 element, so that means if head arrow next is equal to a null pointer, and we're not yet at this case here, I think we're maybe more at this case. If I notice that head arrow next, so here's head, if I notice that head arrow next is null, my list has only 1 element. So what's the sum of a list of 1 element? Well, that's pretty easy. It's just the value of that 1 element. Okay. And then finally, down on line 105, I need to handle the case where the list has more than 1 element, in which case there's the element I'm looking at. That's head, so I'll draw that in. And then there's the rest of the list, the shorter list beginning at head arrow next. So how do I compute the sum of that? Well, let's see. I guess it'll be the value in the element that I'm looking at, so head arrow element, plus the sum of everything else. And I use that recursive call. I call the same function on a slightly smaller list, and I have it do all the legwork for me. And again, okay, so there's this stack of 3 if statements, which is a little bit more verbose than what I had before, but I think this is still really elegant. And I think it also makes it a lot easier for somebody that's used to reading recursion to make sure that the code works correctly. Although you can probably read the iterative sum list function, what if there were a bug? Would it really be that much fun to debug a function like that that's throwing around pointers? Here, I am working with pointers, but because the way I'm breaking it down is a little bit more logical, it's something that's, I guess, higher up conceptually, maybe I can catch my errors more easily. All right, so let's try testing that out. And again, these 2 warnings, copy and filter, are just setting us up for our next video. We try running it, and the number of elements is, so this is our list, 17, 10, 6, and then 10, 10, and 10. The number of elements is 6, which I'll vouch for that. As I said, years of experience tell me that 17, 10, and 6 sum up to 33, so that's 43, 53, 63. That is the sum of the elements. So I've now written a recursive version of count elements and sum list, and earlier in the video, we wrote this recursive insert at end function. All right, but this is all setting us up for the end game here, which is these 2 functions, which we knew to be a real mess iteratively. Let's see if recursion truly pays off by writing copy and filter recursively, which we'll do in the next video.